You have typed git commit thousands of times. It's probably your muscle memory. Stage some files, write a message, hit enter, done. The whole thing takes half a second. But what actually happens in that half second? Today, we are slowing down that half second down to 10 minutes. We'll trace a single git commit from keystroke to stored object. Once you see it, you'll realize Git's design is shockingly simple. Let's trace the journey. Git views your project in 3 layers. Your working directory, the actual files you edit, the staging area, also called the index, where you place things for the next commit, and the repository, the Git folder where Git stores everything. Here is what most people miss. When you ran git add, Git didn't just make a note to include that file later. It immediately took the contents, compressed them with zlib, computed a SHA-1 hash, and stored the result as a blob object in Git objects. Your file contents are already in the repository before you commit. The commit just organizes them. Now, a blob has an interesting property. It stores the contents of a file, but it doesn't store the file name. A blob doesn't know if it came from main.js or utilpy or readme.md. It's just raw content, nothing else. Why design it this way? Because it enables powerful deduplication. The hash is computed purely from the content. Same content always produces the same hash. So if you have 2 files in your project with identical contents, maybe you copied a config template or 2 modules share the same license header, Git stores that file content exactly once. One blob, reference from multiple places. And this is how Git stays efficient even in massive repositories. So we have blobs sitting in the object database, but Git still needs to track which files you intend to commit and which blob belongs to which file name. That's where the index comes in. There's a file at git index that acts as the manifest of your staging area. It maps file paths to blob hashes. When you run git status and see files listed as staged for commit, Git is reading this index and comparing it against your last commit. Think of the index as a shopping cart. You pick changes from your working directory and add them to the cart with git add. And the cart tracks exactly what you have selected. When you commit, the cart's contents become permanent. Right before you hit enter, the blobs already exist in the object database. Your file contents are saved. The index knows exactly which blob belongs to which file path. Your manifest is ready. Everything is staged and waiting. Now you type git commit -m, subscribe to ByteMonk, and press enter. First, Git checks if there is anything to commit by comparing the index to the current head. If nothing changed, it exits. Assuming you have staged changes, it proceeds. Next, Git needs your identity. It reads user.name and user.email from your config. Local, then global, then system. Without these, Git cannot create a commit. It also grabs the current timestamp with time zone. Validation complete. Now Git creates the objects. The first object is a tree. If blobs represent file contents, trees represent directory structure, like folders containing files and other folders. Git constructs a tree from the staging area. Each entry has 4 pieces, starting with the mode, file systems and permissions, the type, blob or tree, the hash, and the file name. You can inspect any tree with git lstree command. You'll see blobs for files and trees for subdirectories. Nested directories means nested trees, all the way down to blobs at the leaves. Here is where Git's elegance shows. Say you modify one file deep in your project, in source components button.js. What changes? Only the nodes on the path from that file to the root. The blob for button.js is new. The tree for components changes because it points to the different blob. The tree for src changes, the root tree changes, but everything else, your test folder, your docs folder, everything untouched file stays identical. Same content, same hash, and Git reuses them. No duplication. And this is why Git handles massive projects efficiently. Most commits create just a handful of new objects along the change path. Everything else gets reused. Git serializes the root tree, computes its hash, compresses it, stores it. Now you have a tree representing your entire project state. Next, Git creates the commit object itself. It's surprisingly small, maybe 200 bytes of text. First line, tree followed by the root tree's hash. The single pointer captures your complete project state. Next, parent followed by previous commit's hash, whatever head pointed to. This creates the chain of history. Every commit points to its parent all the way back to the first commit. Merge commits have multiple parents. Then author and committer info, name, email, timestamp. Usually identical, but different when someone applies your patch or during release or during rebases. Finally, your commit message. That's it. Tree pointer, parent pointer, author, committer, message. Git hashes this, compresses it, stores it. That hash is your commit's permanent identity. At this point, the commit object exists in the object database. But here's the thing, it's just sitting there. Nothing points to it yet. If you try to find it, you would need to know the exact hash. It's like having a new page in a book but no entry in the table of contents. We need to connect this to commit to your branch. So how does Git know which branch you are on? There's a file called head in your Git directory. Open it up and you'll usually see something like this. That's Git saying the user is currently on the main branch. Now, Git follows that path. It goes to git revs head main, which is just a plain text file. And inside that file, a single line, the 40-character hash of whatever commit main was pointing to before you ran this command. That's your parent commit. That's the commit you were on 5 seconds ago. To complete the commit operation, Git simply overrides that file with the hash of your new commit. The old hash gets replaced with the new hash, one line changed in one small text file. And that's it. That's how branches move forward in Git. This is worth pausing on because it's so much simpler than people expect. A branch isn't something complex data structure. It's not a copy of your code. It's not a series of divs. A branch is literally a text file containing a commit hash, 40 characters and a new line. That's the whole thing. This is also why commits are immutable but branches are mutable. The commit objects themselves never change. Once created, they exist exactly they are forever. But branches, they are just pointers. They get updated every time you commit. The branch moves forward while the commit stays fixed in place. And this explains why creating a new branch in Git is instantaneous. No matter how big your repository is, Git isn't copying files, it isn't duplicating history. It's creating a 41 byte text file containing a hash. That's the entire cost of a new branch. Now the chain is complete. Head says you are on main, the main branch file contains your new commit's hash, and your new commit's parent field points back to the previous commit. Everything is connected. Now that you understand how commits work, basically content address objects linked by mutable pointers, it changes how you think about shipping code to production. Speaking of shipping code faster, that brings me to today's sponsor, Graphite. Here is a problem every developer faces. You finish a feature, open a PR, and then you wait. You are blocked until someone reviews your code. You could start the next thing, but then you are managing multiple branches and context switching when feedback comes in. Companies like Meta and Google solved this years ago with something called stack diffs, and Graphite brings that workflow to GitHub. Let's say I'm building a recommendation engine. I create a PR for the caching layer, but instead of waiting, I immediately stack another PR on top for the recommendation logic, then another for the API endpoints. 3 focus PRs that can be reviewed in parallel. When the first one merges, the stack automatically adjusts. I never stopped making progress. Now, you could do this manually with Git, but it's painful. Constant rebasing, updating base branches, managing dependencies, Graphite handles all of that automatically. So when I run GT sync, it restacks everything. When a PR merges, it cleans up the branches. The CLI shows my entire stack with GT stack view, and creating a new stack branch is just GT branch create. It works with your existing GitHub repos, and you are not leaving Git, just making it way less tedious to manage stacks. The result? Small PRs that get reviewed faster, features that ship incrementally, and you're never sitting idle waiting for approval. Graphite has a free tier you can try. I'll drop the link below. Seriously, once you start stacking, the old way feels broken. One more thing Git does, updating the reflog. Every reference change gets logged in Git logs. Each entry records old hash, new hash, who, when, and what operation triggered it. The reflog is your safety net. Accidentally resetting hard and losing commits? They are not deleted. The objects still exist. You just lost the pointer. Run git reflog, find the hash, recover it. Reflog entries persist 90 days by default. That's your window to undo catastrophic mistakes. So let's recap that half second. Git read the index, validated against head, grabbed your identity, constructed a tree reusing unchanged subtrees, created a commit object, with tree pointer and parent pointer and metadata, hashed and stored both objects, updated the branch references, and logged everything in the reflog. All of that instantly. No database, no complex binary formats, just a folder of compressed text files. In fact, you could implement basic Git in just a few hundred lines of code. So next time you run git commit, appreciate what's happening in that split second.